Hi, this is Professor Fernandez. We're going to work on class notes A in lesson 13. The point of this class notes is to, as it says right above it, illustrate how to use the theorem. I'm going to scroll up here, theorem 13.1.1, to develop a procedure for solving equation 13.2. This is the eigenvalue eigenvector equation. So let's get started. Here's what I'm going to do. I'm going to start with the E vector E value equation. So let's say AV equals lambda V. And what I want to do in this class notes is try to figure out how to solve this, right? I don't know the matrix A. I don't know anything. I don't know lambda. I don't know V. Might not know where to start. But what I'm going to do here is subtract lambda V to the left-hand side, leaving me with the zero vector here. And now I would like to factor out the V, right? Because I see that the V is common to each one of these terms. But if I write just this is generally not going to be true. Why is it generally not true? Because lambda is a number and A is a matrix. So this would be like trying to, here's a random matrix, trying to calculate this difference. It doesn't make sense, right? We haven't defined that. What would I do with the 14? Do I excuse me, subtract it from every element? Do I subtract it just from this one? It's not clear. We have no definition for that. So to factor out the V correctly, what we need to do is we need to recognize that if I were to write out this portion, AV, I would get A11 V1 plus A12 V2. So I'm just writing out here the result of multiplying a matrix A times a vector V. So we've done this a few times in the course now, so I'm skipping the intermediate details. If I were to write this part out, it would be lambda V1 all the way down to lambda Vn. Okay. So if I then thought a little bit about what I would do next, if I combine these two, I would have A11 minus lambda times V1, right? So this one has a V1, this one has a V1. We're subtracting it, so that's why I factored out that quantity. But then nothing else would change in this first row, A12 V2 all the way up to A1n Vn. In the second row, over here is a lambda V2. So what would happen in this second row of the new matrix? I would have A21 V1 plus, and then I would factor A21 minus the lambda V2 plus all the way down to A2n Vn. All right, and then the very last row, you can maybe see what's happening here. This, when I subtract the lambda Vn up here, oops, and I realize that this should have said an n over here. This, when I subtract the lambda Vn over here, is going to pair with that one. So I'm going to be able to factor out here Amn minus lambda Vn. Okay, so why did I do that? I did that to convince you of the following fact, right? What does this look like? How can I express this as a matrix? Well, notice what's going on. I am subtracting lambda only from the diagonal of the matrix. No other terms in the matrix that are not in the diagonal have lambda subtracted. So that is a very good clue as to what the quantity AV minus lambda V really looks like as a multiple of V. Okay, so first of all, it has all of the same A entries that were in the matrix A times V before. So there's definitely an A here. But then we have now realized that lambda is getting subtracted only from the diagonal, right? So it's definitely being subtracted and only from the diagonal. So I need to write out a matrix that only has lambda in the diagonals, right? So that looks like this: lambda, 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 and then zeros everywhere else. Okay, so that matrix equals lambda times this matrix, which has ones everywhere else. Ones along the diagonal and zeros everywhere else. Okay, and I did that factoring of lambda again by the definition of what it means to multiply a number times a matrix. You multiply it into every entry of the matrix. But in this particular matrix, there are so many zeros right here that when I multiply lambda, I only end up changing the diagonal, and that results in that diagonal of lambdas. Okay, this matrix is called the identity matrix, and I'm going to put I n by n. This is the matrix which has 1 along the diagonals, 0 everywhere else. For example, I 2 by 2, the 2 by 2 identity matrix looks like this. Right? I 3 by 3 looks like this. Okay, and then so on and so forth. So that is what I'm doing for this last little bucket here, right? So we determined that I'm subtracting lambda only from the diagonals. So I want to use this matrix, right? So this is effectively the same, it is the same as this lambda times the identity. So I'm going to put that in here. Lambda times the identity, n by n. Great. So what is the takeaway? The takeaway is that I've finally now been able to correctly factor out the v on the left-hand side. So I'm just going to write this over in slightly cleaner form. So now this is a minus lambda I n by n times v. And I'm going to now just make a small notation change. I'm going to get rid of the n by n, right? It's understood now that, remember, if I subtract matrices, it's understood that they have to have the same size. All right. So, you know, the calculation I did up here assumed a matrix of size mn. I should have said that it's a square matrix so that all of the subtraction of lambda would have worked out. So that should have been square. So down here, I'm going to go back and finish what we are going to try here for solving the eigenvalue eigenvector equation. So I started with this, and then I have now moved over the lambda v term, and then I have now converted it into this form. Great. So let me call this matrix, this new matrix, B, so that my new system is BV equals 0. So you might recognize this from the theorem that was right above this class notes, this one. So now this is where we're going to invoke this theorem. So let B be an n by n matrix. Consider the system of linear equations BV equals 0. Same one we're looking at. Then the system has a non-zero solution, right? If and only if the determinant is 0. So I say a lot about the fact that we want non-zero solutions for our, to find the eigenvectors and the eigenvalues. And that's exactly what this theorem is guaranteeing us, provided that the determinant of B equals 0. So then I'm going to come down here and I'm going to say, okay, great. So we have this condition, BV equals 0. So by theorem 13.1.1, this system has non-zero solutions if and only if determinant of B equals 0, right? And what was B? Well, B was up here, right there. So this turns into determinant of A minus lambda I equals 0. And that explains this definition down here. So that gets us this condition. Okay. So the determinants of A minus lambda I is going to yield what's known as the characteristic polynomial. And we'll see that in the examples, and we'll see that in the rest of this lesson notes. But this is the point of this class notes, to get us to this condition, right? This is how we are going to find the eigenvalues lambda that we will later substitute back into the matrix and row reduce to find our eigenvectors.